On this episode of This Week in Space, we're talking about building homes on the moon. Stay with us.
Podcasts you love.
From people you trust.
This is Twit.
This is This Week in Space, episode number 117, recorded on June 28th, 2024, A Home on the Moon. Hello, everyone, and welcome once again to This Week in Space, the Home on the Moon edition. I'm Rod Pyle, editor-in-chief of Ad Magazine for the National Space Society, and I'm here with our honored guest co-host, Isaac Arthur, who happens to be the president of the National Space Society, but more importantly, the creator of Science and Futurism with Isaac Arthur. Isaac, since this is your first time co-hosting, tell us all a little bit about your channel, if you would. This is on YouTube.
Well, I'm looking forward to filling in for a while Tarek's out, and I've been hosting Science and Futurism with Isaac Arthur for 10 years this September. 10 years. Wow. And it's been an amazing time. We do a weekly episode and some others too. We're up to almost 700 total episodes. And we probably have our biggest focus on space, but we also just look at everything from transhumanism to aliens and Fermi paradox theories to what sort of technologies are right over the road in the next few years even. And while we do tend to have a bit of more distant focus in the future, we do try to keep everything very grounded in science. We love to talk sci-fi, but we like to use that as an example as opposed to, the main point. How can we make these things from our favorite shows, from Star Trek, from Star Wars, actually be effective, useful, make them become real or something close enough to them? And so that's been our focus for, again, going on 10 years and 700 some episodes. So it's been a great time. Also became the president of the National Space Society last year, and I've been loving it. It's such a great fit. The National Space Society is just, I used to think it was an organization just for astronauts, and I found out it was for everyday science geeks too. I love the group.
But we do have both. And I'll just add about your channel, which you, I don't think mentioned, you're coming up on 800,000 subscribers. Is that right?
800,000 subscribers on YouTube and some more on some other platforms. We got the podcast version's got a couple 100,000 too. And it's just amazing. When I started the show, I didn't think we'd ever find even 1,000 people who were interested in the topics. And turns out there's a lot more of them out there. So it's been a wild run.
And I just want to say, as a guy who worked on Star Trek in the 90s, where we had to sort of meter out the visual effects in little tiny bits because they were so damned expensive and hard to do, which resulted in a lot of time watching the captain, or in this case, it was D Space Nine, so Avery Brooks, bouncing in his chair as they're firing photon torpedoes at things. Your show has eye candy from beginning to end, and it's great stuff. And it really, it makes it so much more fun to watch than it would be otherwise. Not that I wouldn't watch you talk, but having that kind of coverage of
it is really amazing cool to have access to those kind of graphics these days. And for the record, I thought Captain Sisko was probably my favorite captain in general. And just by freakish coincidence, I was talking to Morgan Gendo the other day. He was the writer of a bunch of episodes back then, including one of my favorites, the Inner Light. So that era is still the most groundbreaking and fundamentally inspiring era of sci-fi to me. So we get to talk about it an awful lot on the show. And it is ironic that our special effects are about as good as theirs with a tenth of the budget these days.
More like 1/100th. Did you ever see Trials and Tribulations?
Oh, yes. Yeah, that's a great one.
So for that episode, I've told this story before, but we actually had to go down to the salt mines in Utah to retrieve the original negative from the first series. And that was, I think, the first time there was a digital transfer of that material, which was incredible. I mean, I'd grown up seeing it on bad 3/4 inch tape dubs on local TV stations, and seeing, the coffee stains and Spock's tunic and this kind of stuff was just completely amazing. However, the downside, since I was a lowly visual effects assistant, was for positioning purposes. They kept asking me to put on one of those. Well, it's actually a red shirt. I was a red shirt, put on one of the red tunics and stand here and there so that they could figure out where they were going to place the stuff in the shot when they were compositing it later. And I looked like 20 pounds of sausage in a 10-pound sleeve. It just was not an attractive look. And thank God I was cut out of all those shots. They later realized, because this was basically cut and cover, putting the new people over the old people standing in the shot, that because my midsection was wider than the people on the original show, they had to enlarge them a little bit to cover. Anyway, that's stuff you don't need to know. Before I forget, Our guest today is Evan Jensen from Icon Build, which is a brand new company making incredible progress in 3D printing of buildings on Earth and planning to do so on the moon and ultimately Mars. So this is a young company. They only started in 2018. And I think you're really going to enjoy this one because he's an incredibly smart guy. I mean, it's a small company, but filled with smart people and just doing incredible work. Before we get rolling here completely, don't forget to do us a solid and make sure to like, subscribe, and all that other podcast stuff. We are counting on you. And now, fake drum roll. The weekly space joke. This comes from Zimmer4MP on the Discord channel, which you can access if you join Club Twit. The other day, I was interviewing an off-planet visitor. We don't call them aliens anymore. Turns out they eat radioactive materials. I asked what its favorite meal was, and it told me that he loves the fish and chips at Isotope Stadium in Albuquerque. That was a sympathy laugh because Isaac's sitting there looking at me like, what the hell are you talking about? So there actually is a stadium in Isotopes Park in Albuquerque, which I assume dates back to the development of the atomic bomb. And apparently they do serve fish and chips, or fish and chips, as the case may be. Now he gets it.
Joke.
It's like,
Fridge
what
joke,
are you talking about? It's an Adam joke.
Some kinds, those are the best kind.
Maybe not this case. Well,
It's like
please,
a hangover. You know?
please, everyone, save the cosmos and us from our own humor. Although I thought that was a pretty good one. So thank you to Zimmer4MP. In any case, send us your best, worst, or most indifferent space joke to twis@twit.tv. That's twis@twit.tv. And now to some headlines. Are you ready, Sir Isaac?
I am.
All right. First one is bringing ISS home one way or another. NASA has selected SpaceX to deorbit the International Space Station for them at the end of the decade, around 2030. The contract is for $843 million, which is pretty cheap by these standards, for SpaceX to engineer a custom vehicle that will operate as a one-shot deal. All it's got to do is nudge the space station down out of orbit and have it re-enter. And the trick of this is, of course, you want it to re-enter so that it ends up in Point Nemo, which is this area in the center of the vast Pacific Ocean, where you want this thing to come down so it doesn't come down on us, because some pieces of it are surely going to survive re-entry. Have you been keeping up with this?
A little bit. I remember from when we had Mir come down. Oh God, how long ago was that? Like at least a couple of decades.
Yeah.
But when that came down, and usually we try to deorbit things that goes that area. There's always that big question of, is there some way we can, not lose this valuable piece of our history?
Right.
It's a tricky question. It's like, well, we're going to spend almost $1 billion to blow up a piece of our history, basically. And it feels wrong, but there are so many limitations what we do about debris these days, which, has been a serious concern just of late. I think with space debris involving that Russian satellite that had the
that's the next story. Yeah.
And so it's a hard one. I know people don't really like the idea of losing the space station that way, but it has lived far longer than we were really expecting. It's done good like Voyager or Pioneer. It's still getting usage out of it, but that time window is coming to a close. And at a certain point, it will be hazardous to even keep people on board that as we kind of learn to the shuttle.
Well, and you bring up a good point. I got a fair amount of email over the last couple of weeks about this. And of course, there's all kinds of conversations online about save the space station and can't we use it for a spacecraft to go to Mars and that kind of thing. And I think it's important to remember, and there's a white paper that NASA put out recently that really talked about in some depth all the options they looked at, including reuse, bringing pieces home to put in the Smithsonian and so forth, which still isn't entirely off the table, but I think it will be shortly. But, it's important to remember by the time this thing is brought down, it's going to be 30 years old. More than that, however, the technology was baselined at the latest in the early 90s. And a lot of it was from the 80s. So this is old tech. It's been up there a long time. Space is a harsh environment. At this point, the astronauts are spending half their time, and an hour in the space station for one person is really expensive, doing maintenance and repair. And although they replaced a lot of stuff, one thing this paper noted was what you can't replace is primary structure and truss work. And although it hasn't been as big an impact as they thought it might be, the repeated dockings and undockings and repositionings of the space station when there's, the potential for an impact from orbiting debris stresses that structure a lot because, of course, it had to be built. They had this complex calculus of it's got to be as light as possible so we can launch a lot of it with the shuttle, which had a pretty limited cargo capacity. But at the same time, it's got to be strong enough to stand up to repeated impacts. So it's sort of like an airliner with a cycle of takeoff and landings. It weakens the structure after a while, and this is another factor in the space station. And there's a lot more to this conversation, but the bottom line is it served us well, and 30 years old isn't old for people, but it's old for space stations.
Yeah, it rubs the wrong way. It's like with the rocket boosters, you get those all the way up into space, and then you put an effort to knock them back down. We're always looking for ways to try to make those work again and use them as space stations. We look like, could we use one of the boosters and turn it into space stations or link them together on a ring? And I love the idea. Everyone loves the idea if you can find a way to do it, but people tend not to think about how much structural damage something like that takes while it's blowing through the air. They are often in pretty bad shape. We're using them as hard. And the same situation goes with the space station. It's been sitting up there soaking up radiation, getting docked with, getting whacked around, not getting much external maintenance for so long now. And there's a point at which it gets easier to bring something else up there. And we have a lot of equipment up there you really could not replace anywhere with newer stuff without it being a very, very difficult process. So it's got its life cycle, and now just the question is, should we keep it around as a potential hazard so we could maybe have a museum of it one day? And I have to admit I'm on the fence about that, but it's served its usefulness as an actual resource facility at this point. The question now is just, do we get it out of there so it's not a hazard, or do we try to preserve it to make it a historical relic? And I think that we've made that decision at this point. So,
yeah, I think so too. I guess the only other thing I'd mention is, it's expensive to launch mass into space. That cost is coming down. If it could be put in a large, high altitude graveyard orbit and maintained as just a source of raw materials for that eventuality when we can actually snip pieces off it and smelt them into new pieces of rockets and whatever else you want to build, that would be great because it's a big source of stuff. But of course, you'd have to take it apart and take out all the wiring and the instrumentation, and it's just not something NASA's looking at. So
also, I feel like cannibalizing a relic at that point in time too. It's like, let's see if we can take the frame off the Mona Lisa and reuse that.
You sentimentalist. Oh,
a little bit, yeah.
Yeah.
I wouldn't want to cannibalize the Apollo landers either.
Yeah, there's hardly anything there anyway. All right, next up, breaking up is hard to do. The ISS astronauts took shelter after a satellite exploded. This was an old Russian satellite that we think may have had a battery that went kabang, but whatever is the case, it exploded. It was no longer functioning. It had just been sitting there for a long time, but it went kaboom, created well over 100 pieces, fairly large pieces of shrapnel. So as is protocol, the astronauts on the space station took shelter in their individual spacecraft in case they had to take off, which in this case was for Starliner, the Dragon, and a Soyuz, to make sure that A, they were protected, and B, if they had to depart in a hurry, they could. Just as a note, an hour later, the all clear was sounded, but there are currently over 7,600 operational satellites in low Earth orbit, many more dead ones, and all kinds of spent rocket stages, chunks of ice from fuel venting, so on and so on. And at least according to what I read, the ISS's safety zone is about 30 by 30 miles. So it doesn't take much to trigger an alert and say, okay, guys, you got to go into safekeeping. And sometimes they move it. In this case, they just went into the capsules. But there's a little bit of a I don't know, kind of a Star Trek vibe to this, or maybe Battlestar Galactica, where it's like you've got to protect yourself from incoming,
Well, so one thing Battlestar Galactica, especially the remake, always did better was showing the sheer amount of damage that debris can do. With Star Trek, a lot of times you're kind of limited because you don't want to mess up that one actual physical model of the ship you have. Space debris is dangerous. We were just talking about that in regard to the ISS. One tiny little piece of shrapnel that fast hitting you at, the equivalent of 14,000 kilometers per second, potentially. Right. If it's the wrong angle, that's going to wreck something really bad. And, again, that's part of why we were retiring the space station. This is a growing problem, but just so much more junk getting up there. And you don't really want to take chances on that one. But because if one of them does hit the space station, they could take the thing out that fast and before we wanted it to. But it was there's somebody coming up on the show in a couple of weeks who's going to talk about orbital debris, wasn't there? I saw that on the schedule.
Yeah, because we're sort of overdue. We had one guest in the past, but it was back in the beta period, so it's been a couple of years. So it's time for us to do that again. Finally, sigh. Starliner weekly update. It's still docked to the space station. So it was supposed to be back by now. This is Boeing's Starliner capsule on its first crewed test flight. And as everyone knows who listens to this, they've had some helium leaks back in the trunk. Helium is used to pressurize propellants. And they had some thrusters fail. So they've done either 5 or 6 resets of the return date so far. And the last one, and this is something we hear with Starliner quite a bit over the years. The last one is, quote, an indefinite delay, unquote. So sometime after July 4th, possibly well after. You know, the problem here is you don't want to keep it there too long because you've got leaking helium, although there's plenty of it. And you don't want it to age out, although it's designed to be there for months. On the other hand, these people have to come home at some point, and the space station's plenty well equipped to support the extra astronauts, and they've got lots to do because there's always a backlog of projects. But, you know, this is a test flight, and the test hasn't gone as well as we liked. I foolishly posted a picture of Starliner with vines growing all over it, attached to the space station on Facebook, and boy, oh boy, did that generate some controversy. I was just putting up a little visual joke, but a lot of people got to sniping at each other, and I almost had to delete the post because it was getting a little too hot in there.
It was a memorable image, though.
I appreciate it, even though it was backwards, right? I mean, that's, thanks, Midjourney. That's the best you can do. But, on the one hand, people are saying, look, new spacecraft take time to work out the bugs and all that. But Starliner's really had a troubled birth. They got more money by almost double than SpaceX did to deliver this vehicle to be able to take people up the ISS. It's been there it is. It's been pointed out that SpaceX had the advantage of having used the Dragon crew capsule for years before Crew Dragon was built, so they didn't need as much money. On the other hand, good old Boeing has been part of the U.S. space program since it started. They worked on Apollo, they worked on the shuttle, they built the SLS. You just wouldn't think this would be that big of a pull. It really has me scratching my head.
Mm-hmm. It reminded me of Star Trek episodes from that picture where they had some kind of space mold or fungus sketch on the ship, and there's been a lot of ones like that in various episodes. But one thing I always remind myself of, to me, every time a rocket managed to get off the pad without exploding, I consider that to be at least a partial success. And so we got to give them that. They got up in space. They did dock. And I think they obviously got it safely down. There was definitely room for criticism because they have had a lot of resources and a lot of challenges. But I say what I always say about this stuff. Rocket science still hard. Anytime you can actually get one of the things to fly at all, it's impressive. But I had some friends who were working on, was it the Peregrine lander, right? Obviously, that didn't work out quite as well as planned, but that was their first flight. You take it as a success just by the fact that it managed to get up there at all. And I don't want to say we just keep throwing things at it recklessly no matter how many challenges we face, but there's a certain part of that. So still rooting for Starliner to get a little bit more successful on future flights. Obviously, this one leaves a bit of room for growth, but not of the space flights.
Very diplomatically said. All right. Let me dip into the mailbag here for just a moment, and then we'll move on. Tim Lazaroff, listener, wrote in about 2 more space songs he wanted to add to our collection from the other week. These are by a group I've never heard of, but my knowledge of pop music is about zero, called Lord of the Lost. One was Leaving Planet Earth, and there was one other. And the singer looks like a goth ghost, but whatever. If it's your taste of music, check them out. Once again, the group is Lord of the Lost. Ever heard of these guys? Yeah,
afraid not.
Good, not just me. Finally, I got multiple why deorbit the ISS inquiries. As I mentioned, one thing I forgot to add to that conversation is NASA's currently spending about $3 billion per year out of their 24-ish billion budget, keeping that thing going. And they'd really like to spend that on going back to the moon and other outside of Earth orbit things. So let's just say it's time. All right. Stay with us, and we'll be right back with Evan Jensen of Icon Build. Go nowhere. All right. We are joined today by Evan Jensen, Vice President of Strategic Research and Development at Icon. How are you, Evan?
I'm well. Thanks for having me.
Thanks for joining us. We met when I came to tour your incredible facility when I was out in Austin, Texas to see the eclipse. Well, to see the bottoms of clouds during the eclipse recently. And it was a real treat. I mean, the trip would have been fine without that tour, but that was just such a capstone. It was put together by the International Association of Astronomical Artists. And we'll put up their website in the show notes. And it was, besides being a pleasure meeting you, I was really impressed with the maturity of your company after, 6 years only?
Yeah, 6 or 7, yeah.
Yeah. So what was the idea? If you could first tell us what Icon Build does and the idea that really got all this started, because it's a pretty unique and progressive vision you guys have.
Yeah, sure. So our founders, Alex LaRue and Jason Ballard, Evan Loomis, sort of got together in a coffee shop somewhere. At least that's how I picture it. Alex specifically had been running a 3D printing service, sort of back out of his dorm room and onward into his post college days. And I think the way he tells the story, he was just sort of tired of making little knickknacks and parts and things like that. Additive manufacturing has grown by leaps and bounds in the last few decades, and he wanted to do something bigger. He said, "What is the limit of this capability?" And that became what we now call additive construction. And so, essentially, that team got together and built the first 3D printer to print a house, and printed what is now the world's first permitted 3D printed structure in North America, what we call the Chacon house. So that was back in about 2018. And then the rest is sort of history. We took that idea and ran with it, and we're working to automate construction to solve the global home building crisis, the global housing crisis.
So across the street from the office where we visited, you have a massive 3D printed structure, but you also have constructed some neighborhoods in Texas already, correct?
Yeah, that's correct. So we started with proof of concept way back when, and really just stretched the design aspects of our prints. We made our printers more capable, more reliable, and a lot larger. So the structure you saw was called House of Phoenix. It's sort of a sculpture to showcase our new printer called Phoenix. It's 26 feet tall. It's a couple thousand square feet, and was done in a single setup with our new 3D printer. So we're pretty proud of that work. It is pushing the limits of what we're capable of, and we hope that trickles back into our main projects, such as the one in Wolf Ranch. It's Wolf Ranch up in Georgetown, Texas, where we printed 100 3D printed homes available on the open market. And we're working on some other projects, for instance, Marfa El Cosmico out in West Texas. So sort of rethinking what the cultural center that is Marfa, Texas could be when you apply 3D printing to that problem.
So you've been working on some the Mars-based stuff with Project Olympus. Could you tell us a little bit about that real quick?
Yeah, of course. So I guess I'll go quick into the brief history of why a construction 3D printing company has aspirations to work on the moon and eventually Mars. I was not a space nerd, as I call it these days, as I've come to find out that's a reasonably well accepted term in the community. And basically, the 5 or 6 engineers at the company at the time, back in I think 2019. We're working away hard on a bunch of 3D printed concrete type problems. And our CEO, who had just finished his master's degree in space resources, sort of busted in and said, "Hey, we're going to do what we've done now on the moon." And of course, I told him he was insane and that it was 100 times harder than anything we had been through. And then I said, "Okay, well, how are we going to really approach this problem?" And I got excited and I wanted to be involved because I didn't know a whole lot about the space environment. It was always felt like something other people did, and that it wasn't tangible for somebody like me. And so I started just, basically offered my nights and weekends, and a few other folks at the company sort of did the same. And we found a lot of interest with NASA, who had actually been trying to 3D print with concrete for Mars specifically, or aimed at Mars, and a bit in the lunar world as well. And that sort of became Project Olympus. And I've been working on it for about 4 years and just having an absolute blast. We were fortunate enough to get some funding from NASA to work on it and to build a relatively small but highly capable team. And we are trying to essentially build humanity's first home in another world.
So just to sort of cue this up, I think I told you when I saw you, I had gone to a demonstration at Jet Propulsion Laboratory right about the time you guys started. I think it was 2017, of an attempt they were doing at 3D printing off-world. And I don't think they had done any particularly sophisticated testing yet with different substrates and so forth, but they were using the athlete robot, which looks like a giant 20-foot high spider with a nozzle on the end of the arm to try and print. And the placement was fairly accurate, although not as accurate as I think is what you're using now, because it's just a big arm. But they're still experimenting with the consistency of the mix and so forth. And it, not to be unkind, because this was early on, but it was really kind of a disaster because the walls were leaning over and the stuff was extruding at different rates, and you had blobs, and it kind of looked like a bad frosting experiment of an 8th grader trying to do something. But that's, of course, where you start. But again, I just, in seeing both the construction across the street from your offices and what you're doing in the lab, it's really astonishing to me, especially now that you say it was sort of an overtime effort, how far you've come. So I think one of the questions that's going to occur to our listeners and viewers pretty early on is, how the heck do you do this off world? So I assume on Earth, you're mixing that slurry with water. Is that right?
Yes, correct. On Earth. So
what do you do on the moon where, there's water there, but it's kind of problematical using it for extruding, isn't it?
Sure. If you don't mind, I'll show a prop because I get this
Sure.
question quite often. So essentially, this is what we use on Earth. This is called lavacrete. It's a cementitious mortar. Essentially, the difference between a concrete and the mortar is the size of the aggregate. Certainly somebody would disagree with me on that simplified definition, but this is what solidifies into what becomes the walls of our homes. And so this material we stack up, and you're talking about controlling the viscosity, especially as you extrude it. So we've gotten pretty darn good at this, in making sure, because it's affected by temperature, it's affected by things like water to cement ratio, all of those different things. So though there are ways to do lunar concrete, if you think about the cement hydration process, it does require water. So when you put water in there and you're in the vacuum of space, or the vacuum of the surface of the moon, essentially the same thing, that's going to just sublimate off and give you all sorts of problems. So even though there are lunar derived concretes, they really require an overpressure situation that we just don't currently have. So I think lunar concretes are going to be incredible in the future. But right now, when we don't have these pressurized structures to build bricks in and things like that yet, I think we started looking at other options. So early on, we sort of did a large literature review and found out kind of what ideas had been studied, what levels of success that they had. We looked across cementitious, microwave processing through thermal energy, laser directed deposition, and molten extrusion as well. So essentially, what we're trying to do, to be clear though, is to live off the land. So for instance, this piece I showed, this is approximately 5 pounds, which would take something like a quarter, just call it $250,000 to get to the lunar surface. So we're clearly not building human scale construction with something quite that large. So what we do is we attempt to live off the land. We call it in-situ resource utilization, or in this case, construction-based in-situ resource utilization. And so this is raw lunar regolith, right? I sort of joke that it's like crushed up coffee cups. So it's a bunch of ceramic material that's been bombarded by micrometeorites for billions of years. And what we do is we try to turn this into something that's structurally sound to build with. So we're not necessarily building sandcastles, but it's not that far off. And so what we've been able to do is to develop what we call laser VMX, which is essentially a laser directed energy deposition system that allows us excuse me, allows us to bring this material through a full melt cycle and re-solidify it into something a lot like a concrete. It's not quite the same, but what we can do is turn the solar energy directly collected on the surface of the moon, put it through our system, and use it to convert the raw amorphous powder here that's not really structurally sound into something that's actually quite an interesting building material. So it's a little hard to work with at times, but it is 100% ISRU, which is something that we're very interested in for the future.
So you wouldn't have to take up a binder or anything with that. It's simply done with heat. Yeah,
correct. So it's entirely thermal energy. And really the hard part about that, other than all the challenges of space robotics and the longevity on the lunar surface with all the challenges there, is actually controlling that material and making sure you get favorable properties out of it. So that's something that we spent the last few years trying to perfect.
All right. You mentioned there's some challenges on just trying to print the materials up there. What other issues you're having there? Is there any advantages in terms of size there or lower gravity causing problems with print deposition, or is it fairly standard, do you think?
So the gravity situation, we don't build quite as free form as we would here. And that has to do with the process and the material. So we're a lot more similar to, if you're familiar with the additive manufacturing world, selective laser sintering or selective laser melt. So we're really building up substrates slowly on top of each other with supporting material on the sides. And so the things like gravity are going to affect, of course, your robotics and the size of those robotics and the payloads they can carry. But more specifically for us, it actually affects the melt pool viscosity, as well as our ability to manipulate that lunar regolith. So you get a lot more lofting, for instance, and your angle of repose could be different the way it stacks up, essentially. So we're working on experimentation and working on better lunar simulants as well to better understand what it's going to be like when we actually have our robotic systems operating on the surface.
Guys are really a full service shop. All right, we will be right back with our next question after this short break. Hold on. So you kind of touched on this, but do you have a sense, 10 years downstream, say, when this is actually happening on the moon, and I suppose it's gravity dependent, but what kind of size limits are there for this kind of construction?
Yeah, so 10 years from now, we hope to have a commercially capable system, essentially. So you're pretty well unbounded by the size of the structure you can make. So far, we've demonstrated that you can continue on a structure that's already been built. So essentially, we can continue extrusion or various joinery processes, our laser VMX process, for instance, almost indefinitely. So you're really limited by the amount of energy that's available to you, as well as the longevity of your robotic systems and how robust those things are. Otherwise, it's relatively limitless. If you want to build a skyscraper, we're going to need a pretty big robot or a robot that can climb the side of the skyscraper. But it's really a matter of what you want to accomplish.
You mentioned skyscrapers there. There's a lot of glass and steel in those. There was some amazing imagery on your website, iconbuild.com. On one of those shows a little greenhouse off the side of the main base. And I found myself thinking, do you see much possibility for printing transparent buildings or translucent ones on the moon?
So there's some, yeah, absolutely. A few notes on that. One of the things we can do is build what I would call a hybrid structure, where essentially you're bringing a decent amount of the materials, things like an airlock, for instance, which at least in the early days is not going to be something that you would want to trust to fully ISRU based construction. It's just simply better, more cost effective, safer to bring something like that and then integrate it into your ISRU based structure. So something like that greenhouse, you probably very much care about how much light is going through those window panes. And so we would just need to develop the method of joinery such that we could incorporate them in our habitat, or greenhouse in this case. That said, there is ongoing research, and we have successfully produced some semi-transparent materials. So it really depends on how you filter out the materials from lunar regolith and what you're after. So we don't have an immediate need in the short term for printing translucent glass, but there might be a world in the future where we do, and we can develop that tech as well.
Awesome.
Well, and you talk about the future. So growing up, when I was a kid in the 1960s, and of course, read a lot of science fiction, and some of that science fiction was back to the 30s and 40s. And really from the 1930s up until, well, yesterday, you see a lot of imagery, off-world imagery of these big transparent domes on the moon and Mars that would just, let the radiation come banging in willy-nilly and, are kind of unnecessary when you get right down to it, except for maybe a place for people to spend time occasionally while they're soaking up rads. When you're talking about the working with lunar regolith, what kind of thickness of that would you need with that composition to block a sufficient amount of radiation for it to be livable?
Right. So it really depends on the mission parameters and how long the humans are going to be there. I assume you're talking about a human habitation.
Yes. Sorry.
And so generally the way that you handle that is by putting as much mass as you can between the thing you want to protect from radiation and the radiation itself. So it's essentially coming from all directions. There's no hide behind a rock because it's only coming from the sun. That's not the way it works. Yeah. But we did some interesting work early on where we tried to understand the entire lunar environment and essentially what we call architecting from the right. So starting kind of with the end in mind. And we looked at all these parameters, both the thermal cycling, the horrible, relatively horrible from a human perspective, thermal environment on the moon, and the radiation environment, micrometeorites, et cetera. And I think maybe you showed some of our habitat designs, which are early concepts, but they're actually informed by a lot of that type of question, right? So when you need a meter of regolith between you and this sort of ubiquitous radiation coming at you, the best thing to do is to put mass between you and that dangerous radiation. So if you don't mind, I'll show
Sure.
this sort of 3D printed habitat that we came up with. So this is printed out of FDM material, regular plastic here on Earth, but this is intended to be a human-sized airlock here, so you can kind of get a picture of the scale of what we're talking about. And so essentially, we'll be able to print this with the technology that we're starting to build. For instance, our 3D printer here on Earth could print this at this size. Which will be an interesting time when we finally get a chance to do an Earth analog of something like of this size and shape.
Yeah.
But the idea behind here is it's actually sort of topology optimized. So I turn it like this, you'll see a lot of the printed material are actually these buckets. And so we're minimizing the amount of printed material that we need, essentially lowering the energy input to the system, getting more out of our robotic systems in terms of longevity, and lowering the time, which essentially, the energy and the time equates to dollars in some sort of fashion. So we designed it like this specifically so that in the render you're showing, you can see that our robotic system can actually fill those buckets with raw lunar regolith and potentially compacted lunar regolith. And so you end up with that meter or so that you really want for a kind of a medium-term duration human mission, and you get it for a lot less embodied energy. So that's what we're sort of after there.
Okay, and just for people listening to the audio stream, what he held up for us looked kind of like a flat-bottomed donut with a bunch of corrugation in it. So these little pockets or something you could fill with regolith, which is a pretty brilliant use of the material because, as you say, it sort of minimizes the mass input but maximizes the protection that people would get. So that's pretty cool.
So it reminded me a little bit of one of those bundt cake
yes, there we
molds
go.
used, like Jello mold. So exactly like that. But in terms of what that's made out of, since we're not going to be baking it out of flour anyway, we're talking about using lunar regolith. That's got to get scooped up through ISRU processes. Can you tell us a little bit about what the acquisition and processing, so with that, what's the ideal particle size? Are we crushing? Are we sieving? What's the process you envision in?
Yeah, sure. So throughout this project, essentially this NASA-funded project called IMPACT, stands for Moon to Mars Planetary Autonomous Construction Technology. We've been developing this robotic capability, everything from the robot itself down to the toolhead. And the toolhead has a few different features on it, one of which is what we call local excavation and size sorting. And to do that, we use what we call the scoop tamp filter. Pretty creatively named there. It scoops, it tamps, and it filters. But essentially, the particle distribution isn't super critical to us. However, large rocks will affect our process and things like that. So generally, we'll filter out anything greater than, say, a millimeter or two. And then any of the finer powders are generally fine for us. But we put a substantial amount of work in to actually get that system working, especially in terms of filtering, because as a lot of folks know from the Apollo days and the lunar regolith sticking to the astronaut suits, things like that, it has a substantial amount of cohesion and really sharp grain sizes that really just clog up everything, and it's just really a pain to deal with. So yeah, we've essentially developed the system to have self-cleaning systems to clean out the filters and to vibrate in just the right way to sort those materials. But relatively speaking, the top few meters of soil are decently or expected to be decently homogeneous with a decent amount of understood particle distribution, at least from the Apollo days. But as we continue to learn more, we'll continue to adapt. And so essentially we just take the material in the local region if we're building something horizontal like a road or a landing pad. And generally we have enough material in that first few, maybe the first half meter or so, to be able to build a pretty thick substrate there, like a foundation or a road or a landing pad. When we start talking human scale habitats, we're going to need a less local excavation capability. So there's a lot of folks working on excavation at scale, including NASA, of course.
But given what we learned during the Apollo program and what we continue to learn from these robotic probes, I gather there won't be any shortage of building material near most of your work sites.
No, I mean, our houses these days are built out of sand, aggregate, cement, which is made all just of materials that are brought up. So a lot of terrestrial analogs to construction.
All right, we'll be right back after a short break. Stay with us. So you touched on the simulants you work with. How do you design a simulant? I mean, you've got chemical properties, you've got mineral properties, as you mentioned, because there's no weathering on the moon. There's just this constant rain of micrometeorite impacts. These things are churned up and banged around, but they're still very sharp. I mean, is that actually part of the simulant you use, the sharpness of the grains?
Somewhat. I say that because, as you mentioned, the weathering is completely different there. So we have processes here on Earth, like rain and wind, that make sand hit just the right particle distribution that you see. Desert sands, riverbed sands, completely different. So from the terrestrial standpoint, in our primary business, particle size, particle distribution, grain size, and shape is a substantial driver of, like we talked about earlier, our ability to handle the viscosity of the material, things like that. So the cohesion's very of interest to us. So to answer your question, though, how do you design a simulant? There's been a long-standing, very robust community at NASA specifically, and in the academic community as well, with a few private companies as well taking part in trying to design better simulants. So essentially, we're taking the data that we've learned from Apollo and trying to make simulants that replicate those behaviors. So we now have we've identified relatively good places on Earth to get this bulk rock, and essentially we crush it into the right particle size distribution, and we try to get as close as we can to the chemical makeup. And essentially we, the community, I should say, are maybe at 99% chemically accurate. You have to be very careful about moisture contamination. There's bake out processes, things like that, to make sure you remove all the organic materials that aren't supposed to be there. You would never find them on the moon. But once you do that, we have a pretty good idea of what these things look like in terms of their glass content, their mineral content, and so on. So we're able to find materials on Earth that are very similar to what you'd find on the moon, and we just mix them at the appropriate ratios. The nuance there, though, is that a chemically accurate simulant is not the same as a mechanically accurate simulant. And so we're actually working with Colorado School of Mines, for instance, on a project funded by NASA Flight Opportunities called DuneFlow, that's hopefully going to launch here in the next somewhere between 3 and 6 months on a lunar gravity flight, where we're going to study the geotechnical properties or the mechanical properties of the cohesion and the angle of repose, things like that, for both a control and multiple simulants that we're working on, as well as we actually are fortunate enough to, I hope, be able to fly an Apollo regolith simulant. So some non-destructive testing. It's a little easier to get a hold of Apollo simulant. And so that apparatus has been through flight qualification, and we're looking forward to using it to learn more. simultaneously, everybody who lands on the moon is landing somewhere that nobody has ever been. So, so far at least. And so we're looking forward to all the data that's coming out of all the missions, sample return or otherwise, so that we can make better geotechnical simulants.
It seems like a lot of Project Olympus would work not just on the moon, but Mars. What sort of have you looked into doing Mars much, and what sort of challenges do you think you'd have switching from a lunar environment to a Martian environment?
Yeah, sure. So there's some favorable things about Mars. For instance, the robotics are easier to keep cool, stuff like that. Completely different material science, though. So actually, I'm pretty happy because we have a lot of experience working with cementitious materials, concretes, and things like that. And I think those are going to be a lot more relevant on Mars than what we use now, which is the laser directed energy. So you're really taking the pros and cons of those environments, things like really good thermal flux from the sun that, or heat flux from the sun that we're able to turn into energy on the moon. That may not be the case on Mars. So essentially, we're going to take an entirely different approach on Mars than we would likely take on the moon. However, when we say something like moon to Mars, which is something that NASA says quite a bit, it's actually in the project that is our kind of anchor project that we're working on. Moon to Mars really essentially means that the technologies that we practice on the moon and we learn about on the moon, robotics, for instance, extreme environments, dust mitigation, autonomy, all of those things actually apply almost directly to Mars. So when we're building with robots, the material is going to change, but the software should be very similar. And many of the problems that we face with the vacuum environment of space and so on in transit, of course, to Mars, we're going to have solved already to construct things on the moon.
So once you get to Mars, which does have an atmosphere, although it's in name only, does the water sublimate slower that you could use that in your mix, or do you still have to use the thermal method instead?
I'm not yet sure. I do think that concrete on Mars or cementitious type materials is going to be a lot more viable. So that said, for the initial pressure vessels, things like that, pressurized habitats, for instance, I think a thermal energy deposition method would be viable as it is here, terrestrially on Earth. But it's a lot slower and it's a lot more power hungry. So I really think the idea of things like laser welded bricks and things like that, cementitious or otherwise, I think maybe we're going to have to look back into humanity's history and see what was working for us when we had less technology available, and see if we can build the way that we used to build, but with robotics.
And cementitious just means cement-like, right?
Cement-like, yes.
Okay.
So you mentioned the long trip. You got to go from just a few days to get to the moon, but it takes months to get to Mars, and you're doing that in zero gravity. Have you guys done much looking at printing space stations or printing modules in a zero gravity environment, like for an asteroid mine?
So we're just getting started. One of the sort of realizations that we had, we have a relatively small team, so we can't open up our aperture too wide and still be performant. And so what we've realized, though, is that we are making large scale lunar robotics, and in order to get a lunar robotic, it has to also be capable of at least existing in the zero gravity, in the flight-like environment, and the launch environment as well, for that matter. And so there was sort of this realization a year or two ago that we basically have a space robot, and so we need to start looking at things like on-orbit assembly, on-orbit manufacturing, things like that. Because again, the software, the robotics, very similar. However, the process is slightly different. So you don't get the benefit of gravity holding your materials together. So you're looking at things like, for instance, wire additive manufacturing may be more reasonable. But we do think a lot about using lunar-derived materials in orbit to construct things. For instance, large glass trusses, that sort of thing, which I think is very viable because that mass is so much cheaper to get into space than when you bring it out of Earth's gravity well. So we do think a lot about it, but it's sort of future-looking for us.
So there's a lot of discussion in the space settlement community anyway about working in lava tubes on the moon and possibly lava pits on Mars. One of the downsides is that they're apparently at least on the moon, fairly brittle because we see a lot of collapsed, how the rills are formed and so forth. And I'm sure that's something that would be, seismically checked before construction. But if you're talking about working inside a lava tube, let's say, because there's some very large ones apparently, I'm assuming that your technologies wouldn't lend themselves to sealing the lava tube against its interior. But if not, you could certainly build large shelters inside that would arch over and then protect whatever sealed habitats were below. Have you looked at that at all?
Yeah, of course. And I think we can potentially seal a lava tube with our technology. We haven't run through the mission ConOps of doing that exactly. Some of that is because a lava tube is a great place for protection, assuming that we can find the ones that we expect to be there when we show up. But they generally are not, to my knowledge, expected to be in, for instance, the South Pole of the moon, which is where we find water at a higher concentration, at least. So it's sort of a geographic issue in some ways. And so, sure, if we want to do lava tubes in the future, the robotics, they don't care, other than maybe the thermal environment's different at the equatorial regions on the moon. But there's a lot of things. Say you wanted to build a data center inside of a lava tube. Where are you going to get the material to build that? Are you going to bring server racks or are you going to build them? So that's sort of our approach, is to really think through what needs to happen inside there, furniture, other stuff like that. Sure, why not build it out of what's there? I don't know how comfortable a brittle ceramic chair would be, but maybe we should start working on that.
Clearly a bunch of smart people working at your shop, which I admire no end. Okay, we will be right back. Stand by.
So you were talking about different locations on the moon we'd like to look at doing, and obviously there's a lot of desire to go on to Shackleton Crater or the equator or other locations that might be better. How mobile do you think the equipment would be? Are we talking stationary equipment that has to get moved by other equipment, or would it be movable platforms?
Yeah, so generally we expect some reasonable amount of mobility, and it really depends on how we design the mission. What are the requirements? And we'll design to those requirements. We do expect to have this sort of Swiss Army knife approach, though, so that if we do have an asset that can last 10 years on the lunar surface and it's only got 2 years worth of work, of course, you want to use it for the rest of the 8 years because you've already invested in that mass getting to the surface. So mobility is something that we're interested in. That said, this is not like an exploration class rover. So we're expecting for it to build its own infrastructure. And I really like the thought experiment of the rover, or our printer in this case, only ever driving on a road that it's printed. So for instance, all the problems with dust and kicking up plumes and the levitation of dust and all of that that's expected on the lunar surface, we can mitigate that and start working on infrastructure and building out where we want to go next. That said, there's still plenty of room for LTV type exploration rovers, but generally we'll get planted in one spot and try to stay within a 5 kilometer radius, for instance.
So I noticed as I was plowing through your website, you're doing a fair amount of work on robotics. Can you tell us a little bit more about that and how much, what your weighting on that is?
Yeah, sure. So we have a relatively small team, but a little while back when we started looking at how to do this, what we're aiming for by the end of this year, which is a TRL 6 level demonstration, that's technology readiness level. When we start looking at how a system like that comes together, it's got to operate in hard vacuum, it's got to operate in a cryo and a thermal environment, and of course some dust involved there as well. We start looking at the market to see what's out there that can handle those requirements in terms of robotics. And long story short, as we're going into COVID at the time, and you start looking at the offerings that are out there, there's really nothing on the market that could hit our schedule or our budget, much less both of them. So essentially, we just went back down to the actuator level and started designing robotics. So we essentially have made a cryovac capable robotic system And we intend to offer that to the market in the near term, if anybody's interested. But mostly, it's a matter of vertical integration because we need to in order to hit our goals. Eventually, we want to have a full commercial capability down to on-surface mobility, which includes robotics certainly. So we do a lot of our own software, a lot of our own mechanical engineering, electrical engineering, and et cetera in-house.
And just so it's said, for those who haven't visited the facility, which is probably just about everybody, the robotics are impressive. I mean, when I went in, I expected something the size of Pathfinder, maybe a microwave or something, but you guys have these huge robotic arms that are kind of nudging up to the class of what the shuttle had on it. And again, just really, really impressive stuff.
I think obviously you're very right to want to focus your aperture down on commercial production of buildings on the moon, but have you looked at any other types of printing there? Like I think Rod had mentioned chairs. Are you considering printing from ISRU plastic materials or just focused on building buildings at the moment?
So it's sort of the order of focus that we're looking at. We prioritize horizontal structures first. So that's things like landing pads, roads. And then we're going to work our way towards protective structures and habitats. And essentially, we're doing that because you don't necessarily need chairs until you have people, for instance. And you don't really need roads until they have somewhere that they need to go. And so we're really kind of focusing a lot on landing pads. It's an interesting part of the community and the road mapping and our current state of understanding of what the plume surface interaction looks like when you land a lander. So we really want to start at kind of first things first mentality, and we're going to get to the rest of the parts later. Now, something like printing with the fidelity that you would need for wheels or gears or something to that effect, I think we can get there. It's probably just that the robot looks a little bit different, but we can cross those bridges when we get to them. I think 80-90% of the technology, the process, parameters and such look pretty similar. So
yeah, and it's interesting, the conversation around rocket plumes has really blossomed in the last few years. It was something that I'm sure people were, I know that Phil Metzger and others in Florida were working on it, but for those of us in the journalism trade, we knew it was an issue, but had no idea how big an issue it was going to become. And the problem for anybody who hasn't been following that, and we have an article coming up in the next issue of Ad Astra magazine that our resident deep diver John Cross has done. That's, I think, probably 4,000 words. So it's a read. When a rocket plume comes down the surface of the moon, or Mars for that matter, but more so on the moon because of the lower gravity, these particles go streaming out really fast. Some of them, I guess, can actually reach escape velocity. And this was seen on Apollo 12 when the astronauts walked over to the nearby Surveyor robotic lander that had landed there 2 years earlier in 1967. And upon examination, once they brought some of the pieces of Surveyor home, they saw that it had actually been scoured by dust particles just from this little 16,000-pound thrust engine on the lunar lander, on the lunar module. So when you start getting larger spacecraft coming down, larger landers, it becomes a real problem. And I know there's tons of work being done on landing pads. Some of them, they're even thinking maybe they can deposit by the lander as it's coming down. But clearly, having something robotically built ahead of time by folks like you before we get there would be a real plus. Can you tell us about the Moonbox?
Sure.
What's a Moonbox?
Yeah, so essentially, we are looking to do the best we can do on Earth. I mentioned the Project Duneflow, which is really working on lunar simulants. And so once you have a simulant, you need somewhere to put it, somewhere to interact with it. And so the Moonbox is essentially part of our laboratory space that we are converting into a big simulant bed. And so that's going to allow us to do things like 3D print in there with, it would be atmospheric conditions, but we can really start to go to human scale without having to be in a large vacuum chamber. So controlled lighting, dust control, things like that. So it's really just a capability that we have here in Austin, Texas to help us get better at working with dirty robots. And so essentially, it's a room with glass windows, but it also has blast doors so that we can close it all down and work on remote operation autonomy of our robotic systems. It's a big sandbox that you get to play in, basically.
Okay.
We were talking about the lunar regolith again getting blown up all over the place, and I'd done an episode recently where we talked about trying to grow plants in the lunar regolith, and one of the problems they have is compaction, and it's always hard to get a good simulant. Your company also does make lunar simulants, do you not, to sell to others?
Correct, and we just started that, and we've worked with Kevin Cannon at Colorado School of Mines, who's been incredibly helpful, as well as the simulant group out of NASA, to be able to build essentially a cost-effective lunar simulant that we can get in bulk. So feel free to reach out if you have needs there.
So we can actually buy this in the future.
You can buy it right now. We prefer not to sell it as a novelty. It's really, for the scientific community and folks that are really driving us forward, because there are limited resources available in terms of mining, in terms of our ability to produce it is at a quality standard that's high. But yeah, you can buy it now.
So another fascinating part of your website, which I found absolutely amazing, and I assume it isn't extended off world yet, but can you tell us a little bit about, I hope I pronounced this correctly, Vitruvius, your AI architecture model?
Yes, sure. So Vitruvius essentially is a way to go from the intent for somebody who wants to build a home through the design. So it's aware of things like a family size and what your budget is, and where you want to build the home, as well as architectural styles that you may want to employ. Maybe you like the brutalist style, or you want a Gothic cathedral themed home. And essentially you can go in and talk to it as AI allows us to do in this modern world. And it'll design a home for you. And so we're working currently on taking it beyond design architecture into the full-on build instructions, so that we can go from a design to a full-priced home with all the way down to printer instructions. So then we can drive the budget, the schedule, and actually hook you up with a builder that will be able to help you make it real.
So this means I can finally buy. So I live in Southern California, where water is a novelty. We have to bring it here. And I can finally build that house up in the mountains where it hasn't burned for 110 years. I can build my fireproof house up there and be the only one left standing on the block when the flames roar through. Does that sound about right?
That's the idea. Yeah, absolutely. And we have a home design, I guess you call it a design language or specification, specifically for areas where wildfires are more problematic than others.
Really?
So yeah, absolutely. Look for Firehouse and Stormhouse on our Codex, which is our catalog of homes. So again, Gulf Coast regions, if you have flooding, for instance, we are far more resilient to things like flooding. Whereas drywall, you have to rip it all out, things like that. With our homes, we're in a lot better shape there. So yeah, we're especially good in locations where you value resiliency of the home.
So I have to look that up. I just had some flooding at the lower level. We just had a big storm go through Ohio. But speaking about water, I saw the Moon Water Ranch concept. Is that a test theater for you guys have in Texas, or can you tell us more about that?
Sure. We have a good presence out in West Texas, generally speaking, and we anticipate doing a lot more printing out there. It's just sort of a cultural favorite of ours. Of course, we're in Central Texas here in Austin, and going out west of the desert's just a fun thing our CEO likes to do. And so we have a ranch out there that's available for remote autonomy testing, and we hope to actually build an analog moon base out there at some point. From the local materials there. So we'll see how that goes. Maybe it's closer to a Martian habitat based on topology and the weather in the soil. But yeah, it's just a capability that we have to go out and test.
So here's the big wrap-up question that I always like to ask, and it can be either from your perspective or the company's perspective, or maybe both. What's your big vision here? What do you foresee in terms of how you're going to either on Earth or off. Of course, we're a space show, but either is welcome on how this is going to play out in the future for you guys.
Yes, good question. So terrestrially, we have a global housing crisis. So that's really the mission of the company, is to use robotics, automation, and AI to solve that. We have a big problem where the demand is not met by supply, and we're lacking skilled labor. And there's more people who want homes than have them, and that's pretty sad for a humanity that is spacefaring at this point. And so, what we hope to do in space is really just, the way I think about it. I was flying across the Atlantic Ocean just yesterday, actually, and it was air conditioned, and I was listening to a podcast, and I'm flying through the sky. So that's like that sci-fi future that somebody in the 1800s or early 1900s maybe thought about. So off-world, what we hope is that we can make that real for somebody in the 2100s. What is the sci-fi future that we want? Let's go ahead and start enabling that now with AI and robotics. And the good news is, Icon as a company, our space team is about 6, maybe 7% of the human energy that we put into our day-to-day work. But it actually helps us substantially with our robots and the way we think about autonomous systems, because there's sort of no way around it in space. And so that actually helps us out quite a bit on Earth, and it helps us to really work on just really hard problems. And we have a great team that's able to take our learnings that we work on space robots, apply them terrestrially, and we take our terrestrial robotics knowledge and we apply it. For instance, making Lunar Simulant, we have a batch plant that makes concrete. It's not that dissimilar. So we sort of have a cross-pollination of those things. And hopefully we're just moving the ball forward a little bit every day. And I hope I live to see the moon base.
Me too, brother. but it's more likely you're going to make it than me. Well, I want to thank you and everyone for joining us for episode 117 of This Week in Space, A Home on the Moon. Please don't forget to check out Isaac's YouTube channel, Science and Futurism with Isaac Arthur, where you can watch over 700 hard science videos. That's 700. This man's been busy. And of course, you can always check out the National Space Society at nss.org, for which Isaac is our president, by the way, just recently installed. Evan, where's the best place for us to follow your progress and the progress of the company?
Yeah, just check us out on iconbuild.com. And look us up when you're in Austin and come see what we're up to.
That's a very nice invitation. Isaac, you got to check it out. It's fascinating. And Isaac, what are some of your upcoming episodes of the show?
Oh, we just had one about building artificial planets that came out yesterday. So, and then
that's scaling up a bit, isn't it?
Yeah. We're looking at the Hollow Earth idea, though mostly from the idea of printing a shell board. And then this weekend we'll be having one coming out discussing Roger Penrose's orchestrated objective reduction, the concept of quantum mechanics and free will. So going to a very tiny scale, a planet scale, then subatomic. So,
I had to write about quantum stuff when I was working at Caltech for a very challenging year of news writing. And I still didn't understand it. So I'll have to watch your episode. I understand the basics of it, much less what you'll be talking about. And of course, you can always find me at pilebooks.com or at astromagazine.com. And please remember to drop us a line at twit.tv. That's TWIS at twit.tv. We always welcome your comments, suggestions, and ideas, even if they're not altogether friendly. We don't mind. And of course, space jokes, because we need those. We're always running thin. We love getting them. New episodes of this podcast publish every Friday on your favorite podcatcher. So make sure to subscribe, tell your friends, and give us reviews. And 5 thumbs up or whatever icons they use. You can always also head to our website at twit.tv/TWIS. And don't forget, you can get all the great programming with video streams and everything else, even extra content. It's kind of a secret on the Twit Network, ad-free on Club Twit, as well as some extras that are only available there for only $7 a month. I mean, really, even in Austin, what else can you get for $7 a month? Not much, I say. You've heard Leo talk about the tough times facing podcasters, and this is your chance to stand up and be counted and support the show and the network. Finally, you can follow the Twit Tech Podcast Network at Twit on Twitter, X, and on Facebook, and twit.tv on Instagram. Thank you very much, and we'll see you all next week.